Proposition 62. If there was light from a galaxy that was heading towards us at the time of our initial collision at superluminal speeds, and over the last 14 billion some odd years, it had been getting redshifted, could we someday see a galaxy come into focus beyond the farthest conceivable Z redshift out of nowhere? If so, then it was predicted here first. In particular, if somehow we could determine it is actually blue shifted first. Proposition 63. There are unknown anomalies in the cosmos like fast optical blue transients and red transients. If our universe was still seeing visitors pass through our localized spacetime that originated from some other nested succession of co-moving frames of reference, then we would predict the potential exists for our universe to receive foreign, faster-than-light celestial bodies that could be asteroids, moons, planets, stars, or black holes. When a body in motion receives its momentum from an external nested succession of co-moving frames of reference, it is not breaking any laws of physics if it passes through our universe at faster-than-light speeds. Proposition 64. If the Vasco project received enough volunteers, we could potentially someday find a succession of red transients being created in sequence. And with accurate distance calculations, we can in turn calculate the relative velocity of the object that traversed through a nebulous gas cloud, igniting pockets of gas for brief periods. If that motion appears to be caused by a superluminal object, it would be solid evidence to support successive collision theory. Proposition 65. A head-on collision between a superluminal visitor and a large celestial object would be predicted to release massive amounts of energy very quickly and could be a feasible explanation for some of the otherwise unexplainable, non-repeating high-energy optical blue transients and high-energy gamma-ray bursts that we have encountered. Proposition 68. One of those random degrees of impacts would be minor glances, which would see the majority of an object continue on, but conservation of momentum could leave a fast, hot, swirling plasma cloud behind. Collisions that occur head-on would see the greatest conversion of kinetic energy directly into hot, dense plasma energy. Those in between would see some amount of kinetic energy converted into the angular momentum of the swirling plasma cloud and not just into heat and light and plasma. Proposition 69. Most galaxies were born with an initial angular momentum, and some of the dense centers that quickly became black holes may have started as leftover remnants, thus more massive than all the dense cooling dust and plasma, and able to attract nearby matter very quickly until their respective Schwarzschild radii was reached. The hot, dense energy plasma, even before it became baryons or atoms, would still be drawn in towards fast-growing dense centers, and supermassive black holes of all different sizes should exist at the center of most galaxies. Proposition 70. No laws of physics are broken when two immense, separate, nested, co-moving frames intersect at 16 or 42 times the speed of light. It either caps at twice the speed of light, which is possible, or it could go much higher. With nearly head-on superluminal collisions, the potential exists for a release of energy so hot and dense that when it cools, the amount of mass we end up with is greater than the combined masses of the two bodies that collided. It breaks the laws of physics to accelerate something with mass inside the observer's frame of reference to the speed of light, but no laws are broken if something enters the observer's frame of reference going at or faster than the speed of light. Proposition 71. Our current best guess claims all the mass in our visible universe was once inside a singularity. Although it is possible a single superluminal collision between two black holes may have been the catalyst that forged our pocket of spacetime, I am certain that no singularities were involved. Singularities exist only on paper and in formula, but do not manifest in the physical realm. Proposition 72. When two inconceivably large nested successions of co-moving frames of reference find their paths randomly intersect, it would be rare that they would have the same relative velocities within their shared parent frame of reference. One of them would normally be moving relatively faster, and the other relatively slower. If that was true, then we should be able to decipher in the cosmic web where many first collisions took place, and if so, then possibly the approximate average trajectory of the faster moving pocket. Proposition 73. The first initial superluminal collisions that occur head-on, where mass is nearly instantaneously vaporized into hot swirling plasma, would see one of the two masses push through and continue on its trajectory, albeit a little slower, even if it's pure plasma in motion at faster than light speeds. As it slows down and or cools, we would predict strands to branch off, and then as they cool even further, for smaller substrands to branch off. Proposition 74. Cosmic filaments and supercluster strands would have widths that would be related to the original masses of the colliding objects, while their lengths would be related to the original relative velocities of those masses, with most of those initial collisions having similar trajectories at the moment of contact. There should be a discernible pattern in first collisions hidden within our cosmic web. Proposition 75. The brightest points of each supercluster and the brightest cosmic filaments would on average be the points of initial collisions where mass is likely to be denser. The densest galactic, not stellar nurseries, could be first collision points, while other bright branch points in superclusters could be secondary and tertiary collisions. Proposition 76. Similarly bright and dense tentacle-like strands would be caused naturally by fast-flowing energy with retained angular momentum swirling off as little eddies and branching off. Branching could happen if we had a superluminal flow of swirling plasma, because eddies could create electric and magnetic fields, and then repulsion or attraction could cause the eddies to slow down and branch off. Those eddies are the very first moment where nested co-moving frames of reference begin to reshape another pocket of spacetime. Proposition 77. It would be interesting to see if galactic rotations followed a similar direction if they appear to be part of a supercluster's substrands. If so, that might be another testable prediction of successive collision theory. Not all substrands would follow that rule, but in theory, many should, while fewer would be the result of post-tertiary collisions. Proposition 78. If the initial collisions did happen with kinetic energies far beyond twice the speed of light, then branches could be the result of an initial collision vaporizing mass into a state of matter we don't even know about, and being carried forward by the more forceful partner as a stream of hot dense energy. It could then, in theory, have separate branch points as it slowed down before it even hit the speed of light, and then final branch points where it slowed down to the speed of light. Not sure if this would be considered theoretical or hypothetical, but I guess that depends on how well received the rest of the propositions end up. Proposition 79. Spiral galaxies are how almost all galaxies likely first form. The leftover angular momentum of some prior succession of collisions leaves hot, swirling balls of hydrogen and helium, potentially dusted with all sorts of remnant gas or dust, hurling through space. Then, the field equations of the general theory of relativity turns that ball first into a disk, hurling through space, and then into a nested succession of co-moving frames of reference, each hurling through space-time, playing follow the leaders. Proposition 80. The cosmic web, great arc, great walls, superclusters, slowly rotating superfilaments, supervoids, and vast areas between filaments are all predicted by successive collision theory. Early mature galaxies, early massive black holes, random galactic density, distributions, and dwarf satellite densities would all be predicted. With SCT, we also get remnants of a cosmic microwave background and baryonic acoustic oscillations, with the majority of all mass being converted first into a hot, dense plasma, then cooling into energetic electrons and hot deuterium and alpha particles first, before finally recombining back into atoms. Proposition 81. Someday our best simulations will remove the assumption of a hot, dense center and begin investigating the complexities and nuances of superluminal collisions. If ever a task was invented that would put a real quantum computer to good use, it would be to try all different parameters to successive superluminal collisions until it could come across one or two possible scenarios that vaguely resemble the parts of our universe we can still see. This is where AI could extrapolate potential physics we have no way to ever test. Proposition 82. Early supermassive black holes and galaxy distributions of all different sizes and densities would be predicted and easy to explain when random chaos ensued as potentially two dense stellar nurseries passed through each other at 8 or 80 times the speed of light and left our visible patch of space-time behind in their wake. Proposition 83. If it turns out that leftover angular momentum from collisions is responsible for some amount of the current remaining rotation energy, then it would be predicted for some large number of spiral galaxies of all different sizes to share a similar rate of rotation if the initial kinetic energy of the collisions were all similar. Proposition 84. When we apply the lens-thirring effect not just to massive black holes, but to all of the overlapping gravity wells making up a galaxy, then we should not be so surprised that star systems along the outer edges are able to spread out from the center as slowly as they appear to. Overlapping gravity wells form a tensor mesh of gravitational attraction. Proposition 85. Our universe is considered flat, which means there is no discernible curvature, and a triangle made of any size between galaxies will always see the internal angles add up to 180 degrees. Proposition 86. If our visible universe was found to have curvature, it would not mean we live in a torus or a saddle. It would only mean that our patch of space-time was inside the gravity well of a far more massive structure. Proposition 87. Local curvature to our relative patch of space-time does not dictate the shape of the entire eternal and infinite universe. It would just indicate our entire visible pocket of space-time was likely orbiting something much more massive.